On November 14th, 2023, a spacecraft older than most of the engineers tracking it stopped making sense. Voyager 1, more than 15 billion miles from Earth, farther than any human-made object has ever traveled, began sending home a stream of ones and zeros that meant nothing. Not silence. Something worse than silence. A signal that arrived on schedule, carried the right frequency, passed every basic check, and said absolutely nothing coherent at all. For the first time in nearly half a century of operation, NASA's most distant emissary was talking, but it had, in effect, forgotten how to speak. The people who noticed it first were not scientists in white coats, standing before giant screens. They were a small, aging team at the Jet Propulsion Laboratory in Pasadena, many of whom had spent decades of their careers with this one mission, some of whom had joined the project when Voyager 1 was still inside the solar system, still decades away from the boundary of the sun's influence. They watched the telemetry come in and felt something that does not usually get mentioned in official press releases: quiet dread. Because at over 45 years of continuous operation, every single day this spacecraft functions is a day it was never designed to see. To understand why this moment mattered so much, you have to understand what Voyager 1 actually is, and what it has already survived. Launched in September 1977, it was built for a 5-year mission to fly past Jupiter and Saturn. It did that, and then it kept going. It sent back the first close images of Jupiter's chaotic storms and discovered active volcanoes on the moon, Io, the first time volcanic activity had ever been confirmed anywhere in the solar system besides Earth. It swept past Saturn and revealed the intricate braided structure of its rings in a level of detail no telescope on Earth could ever hope to match. Then, rather than settle into retirement the way most missions do once their primary objectives are complete, it kept going. It kept going past the point where its own engineers expected the plutonium power source to fail. It kept going past the orbit of Pluto, past the last icy debris of the Kuiper Belt. And in August 2012, it did something no spacecraft had ever done. It crossed the heliopause, the invisible boundary where the outward pressure of our sun's solar wind finally gives way to the pressure of the galaxy itself, and it left the solar system entirely. Since that day, Voyager 1 has been flying through interstellar space, the space between stars, carrying a golden record of human sounds and images that almost certainly will outlast our entire species. It is, quite literally, humanity's only working outpost beyond the sun's front door. So when that spacecraft suddenly started sending back gibberish, the stakes were not abstract. This was not a satellite that could be replaced. There's no rescue mission 15 billion miles away. There's no way to fly out and physically inspect a machine that takes light itself, moving at 186,000 miles per second, more than 22 hours just to reach it. Whatever was wrong with Voyager 1 would have to be diagnosed and fixed from a room on Earth, using data that took nearly a full day to arrive and commands that took another full day to get back. A single question and answer exchange with the spacecraft took the better part of 2 days. Imagine trying to repair a computer where every "did that work?" cost you 44 hours, and where there is exactly one machine in existence with no backup, no second unit sitting on a shelf somewhere to test ideas on first. The garbled data itself was strange in a very specific way. It wasn't static. It wasn't noise. It followed a repeating pattern which told engineers something important. The spacecraft's radio transmitter was still healthy, still pointing at Earth, still broadcasting on the correct frequency. Something further back in the chain, something inside the spacecraft's own onboard intelligence, was broken. The suspect quickly became the flight data subsystem, one of 3 onboard computers responsible for packaging science and engineering data before it's handed off to the radio transmitter for the long trip home. And this was where the real horror of the situation set in for the JPL team. That computer runs on hardware designed in the 1970s, using memory technology that most of today's engineers have never worked with in their entire professional lives. There is no manufacturer to call. There's no forum to search. The people who originally wrote the system's manuals are, for the most part, either retired or gone. For months, the spacecraft sat there, both alive and unreachable at the same time, transmitting a carrier signal that proved it was still listening, still functioning at some basic level, but unable to tell anyone on Earth what was actually happening inside it. Some outside observers began quietly preparing for the idea that this might be the end. Voyager 1 had cheated death more times than any mission in NASA's history, surviving intense radiation belts around Jupiter that were never fully modeled before launch, surviving a temperature environment colder than anything its designers had planned for, surviving decades in a power-starved state that would have crippled almost any other machine. And now it seemed possible that a single corrupted chip, sitting inside a computer no one on the planet had physically touched in nearly 50 years, might succeed where deep space, extreme cold, and decades of radiation exposure had failed. Inside JPL, the mood during those first weeks was described by people close to the project as somewhere between a puzzle and a vigil. Every few days, the team would send a new set of diagnostic commands outward, then wait almost 2 full days for any kind of response, only to receive the same meaningless pattern back again. Christmas came and went. The new year arrived. Voyager 1 kept transmitting its steady, broken signal into the void, a machine technically alive but functionally mute, still obediently pointing its antenna at a planet it left behind before most of the people now trying to save it were even born. This wasn't the first time this exact spacecraft had been counted out. In 1978, less than a year after launch, a stuck switch nearly caused controllers to lose contact with it entirely, before engineers traced the fault and corrected course. In the years since, both Voyager probes have weathered failing gyroscopes, thruster clogs that had to be worked around with fuel lines untouched for decades, and a temperature environment so cold that some components operate well below what their original manufacturers ever tested them for. Every one of those earlier scares had been solved by a workforce that, at the time, still included many of the original architects of the spacecraft, engineers who had personally soldered its circuits and could recall its internal wiring from memory. By 2023, that generation was almost entirely gone from the active workforce, and the team facing this new crisis had to rely on paper archives and institutional memory passed down secondhand rather than direct recollection. In a very real sense, this repair wasn't just a technical challenge. It was a test of whether knowledge itself could survive the retirement of the people who once held it. The instrument now producing the interstellar hum, the plasma wave subsystem, has its own quiet history of near misses. It was this same instrument that, back in 2012, gave scientists their first solid confirmation that Voyager 1 had actually crossed the heliopause. Not through any dramatic visual change, but through a sudden, measurable shift in the density of charged particles surrounding the spacecraft, a shift consistent with leaving the solar wind behind and entering true interstellar plasma. Researchers didn't announce the crossing immediately. They spent months quietly cross-checking the data, unwilling to declare a historic first without being certain. When the paper finally published, it confirmed something almost impossible to overstate. A machine built in the age of rotary telephones had become the first object made by human hands to leave the neighborhood of its own star. That same instrument's more recent readings, published by researchers studying the years of data collected since the crossing, described the plasma density around Voyager 1 as unexpectedly active, not chaotic, but rhythmically, persistently oscillating in a way that doesn't map cleanly onto the models scientists had built before actually having a spacecraft out there to check. Some of the activity appears linked to shock waves rippling outward from solar eruptions, arriving at the spacecraft's position months after they left the sun, still detectable across billions of miles. But even in the quiet stretches, when no known solar event should be disturbing the plasma at all, the instrument keeps registering that faint, steady hum, as if the interstellar medium itself has its own quiet baseline of activity that nobody predicted before Voyager 1 got there to listen for it. But the story of Voyager 1's survival has never really been about the spacecraft. It has always been about the people who refuse to let it go. And this time, the fix came from an unlikely place, a printed schematic. Somewhere in the JPL archives, engineers pulled up decades-old paper diagrams of the flight data subsystem, documentation written by a generation of engineers who are now mostly retired, some of whom no longer walk this earth. Younger engineers had to essentially teach themselves a computer architecture that predates almost every technology in their own lives, cross-referencing yellowing blueprints with the sparse, garbled telemetry still trickling in, piecing together the internal logic of a machine the way an archaeologist might reconstruct a lost language from broken fragments of stone. What they eventually suspected was almost unbelievably small in scale for a problem this catastrophic. A single chip inside the flight data subsystem's memory, responsible for storing a portion of that computer's software, appeared to have failed, likely the result of either an aging component finally giving out or a stray hit from a cosmic ray, the kind of high-energy particle that streaks silently through interstellar space and, once in a great while, physically corrupts a memory cell it happens to strike. Whatever caused it, the result was the same. A chip holding a piece of the computer's operational code had gone bad, corrupting everything downstream of it, which is why the data coming back to Earth looked less like information and more like noise, wearing the mask of a signal. Here is where the fix becomes almost poetic in its audacity. You cannot simply replace a broken chip 15 billion miles away. There's no repair crew, no spare part, no soldering iron in the void. So the team did something else entirely. They decided to relocate the affected code. Instead of trying to fix the broken memory itself, they would rewrite the software so that the specific piece of code that used to live on the dead chip would instead be split apart and stored elsewhere, spread across other parts of the computer's still functioning memory. It meant carefully rewriting decades-old code designed for a machine with less processing power than a modern calculator, making sure every piece would still talk to every other piece correctly, and doing it all without the ability to test it on the actual hardware first, because the actual hardware was sitting in deep space, unreachable except through those excruciating 44-hour round trips. One mistake, one miscalculated address, one overlooked dependency buried in 50-year-old logic, and the fix itself could have silenced the spacecraft for good. In March 2024, after months of painstaking work, the team sent up the first piece of the puzzle, new code containing the relocated instructions for one portion of the system. Then came the wait. Engineers who had built entire careers around this mission sat with the knowledge that somewhere out past the edge of the solar system's influence, their instructions were traveling outward at the speed of light, about to attempt something that had never been tried before on a machine this old, this far away, this irreplaceable. There was no simulator sophisticated enough to guarantee the outcome. There was only the code, the distance, and the weight. And then, on April 20th, 2024, the signal came back. Not gibberish, not a repeating pattern of nonsense. Real, readable engineering data for the first time in 5 months. The room reaction, according to those who were there, wasn't a Hollywood eruption of cheering. It was something quieter and somehow heavier. The particular relief of people who had spent months genuinely unsure whether the machine they'd devoted their lives to was already gone. Over the following weeks, the team methodically repeated the same relocation process for the rest of the affected code. And by the following month, Voyager 1 wasn't just alive. It was back to full scientific operation. Once again, returning usable readings from instruments, studying the strange, largely unexplored region of space it now calls home. What makes this recovery almost unbelievable isn't just the technical achievement. It's the fact that it happened at all, on a spacecraft that has already blown past every reasonable expectation placed on it. Voyager 1 wasn't supposed to still be transmitting in 2024. It certainly wasn't supposed to survive a catastrophic computer failure using engineering knowledge that mostly exists now only in retired brains and yellowing paper archives. But it did. And that resurrection bought scientists something they didn't expect to have anymore: continued access to a region of the universe that no other instrument, anywhere, can currently reach. Because here's the part of this story that rarely gets told with the attention it deserves. What Voyager 1 has been quietly recording out there in the space between stars includes something that scientists still don't have a complete explanation for. Since crossing into interstellar space in 2012, Voyager 1's plasma wave instrument, one of the few instruments still functioning after nearly 5 decades, has been picking up a strange, persistent oscillation in the material that fills the space between star systems. Researchers have described it, almost involuntarily, as a kind of steady hum. Not silence, which is what many assumed interstellar space would sound like when translated into audible frequencies. A tone. A low, continuous vibration in the thin plasma that drifts between stars, present even during periods when there's no obvious solar event that should be stirring it up. Scientists have some theoretical framework for what's causing it. Interactions within the thin, ionized gas that makes up the interstellar medium can naturally produce these kinds of oscillations, but the persistence and steadiness of it has surprised the people studying the data. It suggests interstellar space is not the placid, empty silence many once imagined, but a subtly active environment humming with low-level activity in ways researchers are still working to fully characterize. Every additional month that Voyager 1 stays alive and transmitting adds another data point to a phenomenon that, right now, no other spacecraft in human history is positioned to measure. Voyager 2, its twin, crossed into interstellar space a year after Voyager 1 and is recording its own version of this environment from a completely different direction, giving scientists 2 independent windows into the plasma between the stars. But both spacecraft are now operating past their expected lifespans, both running with reduced power, both facing a countdown that no repair, however clever, can pause forever. The team that pulled off the 2024 recovery worked under a constraint that rarely gets discussed outside engineering circles. They were essentially debugging a foreign, unfamiliar system live on a production machine, with no ability to roll back a mistake. In terrestrial computing, engineers test changes on identical backup hardware before ever touching the real system. Voyager 1 offered no such luxury. There was no twin sitting in a lab in Pasadena running the exact same corrupted memory configuration. Every test was, in effect, a live test performed on the only copy of this particular machine that will ever exist, at a distance where even the smallest miscalculation could not be caught and corrected in real time the way it would be on Earth. That is the quiet, understated bravery buried inside this story. A group of people choosing to act decisively, knowing they had exactly one attempt to get each step right, because the object they were trying to save could not be tested, could not be rebooted from a backup, and could not be replaced. It's worth pausing here to appreciate just how strange this arrangement really is. 2 machines, built in the same factory, launched 16 days apart in 1977 using technology that predates the personal computer, are currently the only sensors humanity possesses in the space beyond our own star's protective bubble. Every observatory on Earth, every space telescope in orbit, every planetary probe exploring Mars or Jupiter or the outer moons is still operating inside the heliosphere, still inside the region dominated by our sun. Only these two aging travelers have actually crossed the threshold, and only they can tell us, in real time, what that threshold and the region beyond it actually feel like. When either one goes silent for good, that direct physical vantage point disappears with it, and it could be decades, possibly longer, before another mission is designed, funded, built, and sent far enough to replace it. That countdown is the part of this story that gives it its quiet, aching edge. Voyager 1 and Voyager 2 are both powered by radioisotope thermoelectric generators, devices that convert the heat from decaying plutonium into electricity. That plutonium decays at a fixed, unstoppable rate, which means the spacecraft lose a small amount of available power every single year, whether anything breaks or not. To keep the mission alive as long as possible, NASA has been switching off instruments one by one for years now, turning off heaters, shutting down entire scientific instruments that once measured cosmic rays and magnetic fields, difficult decisions made not because the instruments failed, but because there simply isn't enough power left to run everything at once. Engineers now describe the mission in terms of which instruments they can keep alive, and for how much longer, rather than which new discoveries lie ahead. Current estimates suggest both spacecraft could still be sending back at least some data into the early 2030s. But every year past that point becomes less and less certain, and at some point, no one can say the exact date, the last usable instrument will finally fall silent, and Voyager 1 will become nothing more than a piece of drifting metal, still carrying its golden record, still moving outward, but no longer speaking to the world that made it. And even after the last signal fades, the journey itself doesn't end. Voyager 1 will keep moving outward long after every engineer who ever worked on it has died, long after the institutions that built it have changed beyond recognition, carrying its golden record of Earth's languages, music, and images toward a destination it will not reach for tens of thousands of years. A slow, silent flight through a galaxy that will have no way of knowing it's there unless, one distant day, someone or something out there happens to notice a small, cold spacecraft drifting past, still carbon copy identical to the machine that left a launch pad in Florida in 1977, still carrying a message from a civilization that, by then, may have changed beyond all recognition itself, or may not exist at all. That, in the end, is what makes the events of 2023 and 2024 so much larger than a simple story about a computer chip. This wasn't a routine repair. It was a small, determined act of defiance against a countdown that everyone involved knows they cannot ultimately stop. A team of engineers, many of whom grew up learning about Voyager 1 as a childhood milestone rather than a machine they'd one day be responsible for saving, dug through paper records written by people who first built this spacecraft nearly half a century ago, taught themselves a dead language of computer architecture, and used it to buy their mission a few more precious years. They didn't do it because the outcome was guaranteed. They did it because the alternative was losing, permanently and without a fight, humanity's only working set of eyes and ears in the space between the stars. And so Voyager 1 continues, right now, at this very moment, moving outward at roughly 38,000 miles per hour, carrying instruments held together by rewritten 50-year-old code, still listening to a low interstellar hum that scientists are only beginning to understand, still transmitting a signal that takes over 22 hours to reach a small team of people on Earth who refuse to stop listening. No one knows exactly how many more years it has left. No one knows what the next failure will look like, or whether this team or the next one after them will be able to improvise a fix for it. What is certain is only this. Somewhere past the edge of everything familiar, a machine built before most of its current caretakers were even born is still out there, still speaking, for now, and every single word it sends back is one more sentence in a story that could end at any time, and that no one, anywhere, has the power to finish for it.